Hi, my name is Xavier Devroy. I'm a postdoc researcher from the Delft University of Technology. And in this video, I will talk about our research on configuration sampling when someone has to test a highly configurable system. So highly configurable systems are really common nowadays. Think for instance about a plugin-based application like WordPress or Eclipse counting thousands of plugins, or even an application of your mobile phone that has to adapt to a different smartphone with different processor, screen size, or operating system versions. So just consider this, with only 33 yes or no options, you can have a unique configuration per person on this planet. So if you have 320 yes or no options, you have more possible configuration than the estimated numbers of atoms in the universe. So just to give you an idea, the Linux kernel itself has already more than 6,000 options. So in this context, exhaustively testing a highly configurable system is usually not possible. So tester will sample a subset of all the possible configuration and test only that subset, hoping that they will find bugs also present in other configurations. And that's where our research comes in place. Why not testing all the configuration? Is it really impossible? And what about the various existing sampling techniques? Do they help finding all the bugs? So to answer those questions, we decided a few years ago with colleagues from the University of Namur in Belgium, the CETIC Research Center also in Belgium, the INRIA and University of Rennes in France, and the KTH Royal Institute of Technology in Sweden, to test a highly configurable system exhaustively and answer the following question. Testing all possible configuration, is it worth it? To answer that question, we picked JHipster, a highly configurable system, and tested all its possible configuration. So what is JHipster? Well, JHipster is a development platform to generate, develop and deploy web application microservices. So with JHipster, you can configure the type of application you want to develop, select the different technologies to include in the technology stack, and start developing your application with a pre-configured project. JHipster is quite complex as a configurable system, so it mixes various languages, including JavaScript, Java, CSS, SQL, etc., and other advanced technologies like Maven, Gradle, Docker, and combine all of them to generate all the possible variants. So our first step toward the complete testing of all the JHipster configuration was the modeling of the configuration space. Unfortunately, a brute force approach using the configurator itself was not possible, as it posed several scalability issues. So instead, we manually inspected the source code of the JHipster configurator that is available on GitHub. We modeled JHipster's variability using a feature model with 48 identified features and 15 constraints. And then we started testing. So for that, we needed two things. First, enumerating all the possible configuration from the feature model and generating the corresponding JHipster configuration files. Second, we needed a configuration-aware testing infrastructure with all the necessary elements to execute the test of the different configuration. Our testing workflow goes as this. For each configuration, we generate the application using JHipster. Then we populate the database schema of the application before executing the unit test. After that, we build the application to produce an executable version, populate the database with data, and execute the integration tests. The infrastructure collects the logs produced at the different step of the workflow to compile the result of the different steps. So in the end, the final cost of the more than 26,000 possible configuration is 8% month to set up the testing infrastructure, more than 4,000 hours, so which is equivalent to 182 days of processor time to execute the test, and 5.2 terabyte of disk space. Out of the 26,000 plus configuration, we observed that 9,376, which is about 35% of the configuration failed. So to identify the underlying faults causing those failures, we used associational learning to associate configuration options with the different failures. We manually confirmed the result using the JHipster issue tracker, and we ended up identifying 5 confirmed faults and 1 new fault later confirmed by the developers. Looking at the portion of failure per fault, we see that the most failures are caused by pairwise interaction faults. Only 1,468 configurations were failing due to an undesired interaction between 4 configuration options. So now that we have the result of the test for each configuration, we can compare the different configuration sampling approaches. We compare the different sampling approach to a random selection of configuration to test, represented by the pink line in our graph. We considered T-wise coverage with a strength T going from 1 to 4, using SPL-cat to select the different configuration. And we see that one-wise only finds 2 faults, pairwise finds 5 out of 6 faults, and 3-wise and 4-wise selection find all the faults. We also use dissimilarity selection to sample configuration as dissimilar as possible. So for that we use pledge with a time budget of 60 seconds for different population size, corresponding to the number of configurations sampled by the T-wise for different values of T. And of course we repeated the execution 100 times for statistical significance. So the results show that dissimilarity sampling is effective for small sample size. Finally, we also apply the most enabled, disabled, 1 disabled and 1 enabled sampling criteria. So in summary, our findings are, well, random is a strong baseline for failure and faults. 2-wise and 3-wise sampling are more efficient to find faults than random. Dissimilarity is superior to random for small sample size. A small sample size is also sufficient to identify most important faults, and there is no need to cover the whole configuration space. And finally, there is no correlation between failures and fault efficiency. In comparison with related work, our case study confirmed that 2-wise and 3-wise offer good balance between sampling size and fault detection, and that most enabled disabled is interesting to initiate the testing of configuration. So different studies also consider either fault or failure to evaluate their sampling techniques. However, our results show that there is no correlation between failure and fault efficiencies. So the assessment of sampling techniques highly vary depending on the metric considered. Finally, several studies are based on fault corpus collected through mining. Those studies can face a problem of incompleteness or error in the corpus depending on the quality of the mining. Our case study in comparison offers a ground truth for sampling approaches since we effectively tested all the configuration. The good news here is that we observed that 5 out of 6 faults were reported in JHipster issue tracker. So fault corpuses mined from GitHub should offer a good approximation of the exhaustive corpus of fault. Last but not least, we interviewed the JHipster lead developer to have their viewpoint on our result and on their current testing practices. So their testing budget, which was 12 configuration at the time of the interview, is mainly based on the execution time that should be kept short to allow a rapid merge of pull requests, the resources available, which was Travis at the time, but also the popularity of the different configuration options. So future research here should investigate multi-objective approaches to take those different aspects into configuration when sampling configuration to test. So in the end, is it worth it? Well, for researcher, yes. It offers ground truths for comparison and allows to investigate the relation between failure and fault efficiency of a sampling approach. It is, however, quite costly, which made JHipster a good candidate for this case study, as it is not trivial but still manageable. So for practitioner, it is not interesting at all. 126 configurations were enough to find all the different faults. A configuration-aware infrastructure might, however, be interesting to reduce the testing costs. So that's it. Do not hesitate to have a look at our paper. It is available in open access. The JHipster dataset is also available on Zenodo and can be used to compare a new sampling approach. And if you have questions, do not hesitate to send us an email. We will be very happy to answer.